In our last lecture we considered the approximate form of solution to Schrödinger equation if the wave vector is at a zone boundary. That is, k is equal to plus or minus pi by a. In this lecture we are deriving wave equation for a general potential. At general values of k, wave equation or central equation is the time-independent Schrödinger equation expressed in Fourier series form, to take advantage of the periodicity of the system. Let U of x denote the potential energy of an electron in a linear lattice of lattice constant A. We know that the potential energy is invariant under a crystal lattice translation. U of x is equal to U of x plus A. Hence the potential energy can be written as a Fourier series in the reciprocal lattice vectors. U of x is equal to summation over g, ug exponential igx. As U of x is a real function, it can be written as U of x is equal to summation, ug exponential igx plus ug exponential minus igx, for positive values of g. The wave equation of an electron in the crystal is h psi equal to E psi, where h is the Hamiltonian and E is the energy eigenvalue. The solutions psi are called eigenfunctions or block functions. Explicitly, the wave equation is p squared by 2m plus U of x into psi is equal to E psi. Explain U of x in Fourier series form. The wave function psi of x may be expressed as a Fourier series summed over all values of the wave vector permitted by the boundary conditions, so that psi of x is equal to summation over k, ck exponential ikx. Remember that potential expression is summation over g, whereas in wave function summation is over k, where k is real. The set of values of k has the form n2 pi by L because these values satisfy periodic boundary conditions over length L. Here n is any integer, positive or negative. The translational properties of psi are determined by Bloch's theorem. Not all wave vectors of set n2 pi by L enters the Fourier expansion of any Bloch function. If one particular wave vector k is contained in a psi, then all other wave vectors in the Fourier expansion of the psi will have the form k plus g, where g is reciprocal lattice vector. Therefore, we can label a wave function psi that contains component k as psi k or psi k plus g. To solve wave equation, substitute equation 25 in 24. The kinetic energy term p squared by 2m into psi. On substituting for momentum operator followed by differentiating, we will get h bar square by 2m summation over k square ck exponential ikx. And the potential energy term, summation over g, ug exponential igx psi x equals summation over g, summation over k ug exponential igx ck exponential ikx. On substituting for kinetic energy and potential energy terms, you will get the equation 26. Each Fourier component must have same coefficient on both sides of equation. The coefficient corresponding to exponential ik plus g is ck minus g. Equation relating coefficients is lambda k minus e into ck plus summation over g, ug ck minus g. Where lambda k is equal to h bar square k square by 2m. This equation is the wave equation of electron in periodic lattice, which is also called central equation. For a particular wave vector k and associated coefficient ck, the only other coefficient we need to know to solve energy is coefficient shifted by g vector, that is ck minus g.